About to leap off this little rope we got going on. He's about to jump. Yeah, this looks good. All right, let's see it. Yeah, swing on out, bro. Oh my.
I was sitting in my differential equations class yesterday, and my professor did a super boring problem on a predator-prey population model. When I heard predator-prey, I started daydreaming about cheetahs chasing gazelles and Star Wars proton torpedoes. So I started thinking about ways a robot could intercept a moving object as fast and efficiently as possible. Let's just imagine that the prey, or whatever target, can only move in one direction for right now just to make things easier. The target has two extreme options. It can either slam on the brakes and stop as soon as possible, or it can full thrust and accelerate as much as possible. Then the Interceptor has three major options as to where it should aim. A predator can just simply aim for the current position of the target and follow it around and cut off corners, slowly catching up to the target. But any smart predator knows that since it's already there and not going to come back very soon, why should it aim for the current position? Another option for the Interceptor is to aim where the target would be if the target would put on its brakes and come to a complete stop. That would be a pretty good juke in any sport, like when a football player slows down or even comes to a complete stop and changes directions. And now the complete opposite scenario would be where the predator would aim if the target were to fully accelerate for the same amount of time that it took it for it to stop. In that case, the Interceptor wants to aim for a good lead on the target. Luckily, I wrote some code in high school to solve the four main kinematic equations. So I'll just use that program to solve all the physics so you guys don't have to worry about any physics formulas. So the first thing you're going to do is import the turtle module. That's what we're going to use to make the graphics of this little simulation. From turtle import all. We're also going to need the keyboard library later, so let's just import it now. We might need the math library later, so let's just import it anyways. And now let's create two different turtles, one being the player and the second one being the Interceptor. T2 equal to turtle as well, and let's make T1's color green. Now let's just set up initial positions for these two as x1, y1, and x2, y2. Let's just make all the velocities 0 to start with. I named them vx, vy, just because we need a time incrementer, which we're gonna have as 1/10 of a second. Now we need the player's acceleration, how fast it can move around, and let's just set that as an arbitrary value of 1 for right now. We're gonna use a unit vector to keep the player at a constant speed, and we can set a equal to 30, so that the player is always moving at 30 miles per hour, and that can accelerate at 1. At all times, it has to be going 30 miles an hour in a combination of both of its x and y velocities. Now the enemy acceleration is equal to 1 as well. We can set it differently later, and then the enemy's constant velocity, we'll just set it as 30 for right now as well. We're gonna have dd as a very small number in Python as 10 to the negative 200. We're gonna have a while loop, so let's just set up a continue value to continue the while loop or not. Now, while this continue is equal to 1, let's just do this while loop over and over and over again. Now we need to detect a keyboard press. We can move around the player. We did the same thing in another video, so I'm gonna do the same exact stuff. If you needed help, just go to the old video. The first two videos I showed you guys how to do all the commands in Python you really needed to know, and we learned how to do the keyboard presses in that video. We're gonna detect up arrows, down arrows, left and right arrows for the player's movement. Okay, now we have up, down, left, and right, and if the key is pressed in whenever this while loop is running, then it changes the velocity by, it adds the a to it, or it subtracts a from it. Since we need to keep this player's constant velocity at 30, we need to actually create a unit vector and stuff, so let's just create the size of both of the x and y components of this triangle and then combine them to make the Pythagorean identity. Okay, I'm just going to store it as this variable sv for right now. How you get a unit vector in the x component is you multiply the velocity of the x by the speed that you want it to go, which is 30, and then you divide that all by the size of the x and y components. So we have vx1 is equal to the a, which is 30 miles per hour, which is what we want it to be in total. We multiply that by vx1. Now we divide that by the sv value, that size of the vector. But sometimes that size of the vector in the very beginning of the program is 0, so that's why I have the dd thing. We need to add in dd. It's a very small value. It's going to barely affect the math at all. Same thing for the y, if you just change the x to the y. Now our player is always going to be going 30 miles per hour in any direction. It doesn't matter. It can't slow down, really. Just how I made the physics for this game. You can make that actually the same as the old video we made. You can make the physics the same as that game. I'm just going to show you guys how to make another way of player control physics. Now we need to update the player's position, which you just do the same as we did before. You multiply our time incrementer by your velocity, and then you just add that onto your position. Same with the y. I'm just going to put some comments in here for once, actually, so I'm going to just keep track of stuff for you guys. Now we want the robot to aim at the player somehow. We went over how the Interceptor can either aim for the current position of the player, aim for the position where the player would stop in a very short amount of time, or where it would accelerate in that same amount of time that it took it to stop. The first correction x is going to be the distance it takes the player to stop. Now don't worry about the physics for this, because I did this all on the paper first. We actually need to go back and keep track of which way the player is moving, and keep track of some pretend acceleration acceleration values for right now. This is just to keep track of the correction accelerations so that if the player is moving backwards, then we know that the correction acceleration is positive A. It makes sense if you actually write out the kinematic equation and solve it yourself. Correction x1 is equal to something divided by another thing. We need negative vx1 squared and divide that by 2cx. This is the x correction for full brakes. Now we solve for the amount of time that we hypothetically have the player stopping fully. We can do it separately x and y. We have time for the velocity in the x is equal to negative vx1 on cx. And now a couple physics things here. Whenever we solve the kinematic equations, we need to solve like 3 in a row basically. We have a full velocity in the x component. Now we can make our second correction of x for the fully accelerating version of the player. Now the derivation of this formula is just messy, so I don't really feel like showing you guys, but you can do it yourself if you go online and look up the kinematic equations and then solve for time and then solve for distance after that. It's a little weird, but stuff cancels out because we have velocities of 0 and stuff. And this is the full throttle in the x, and then you can just copy and paste and change everything to y for the y. Now instead of just aiming for either one of them, what we can do is aim for the middle of the 2 points. We have the point where it takes the player to fully stop and the point where it takes the player to fully accelerate. And if you remember on my bike, the distance it took me to stop versus the distance it took me the same amount of time to accelerate really fast, I was all the way over here. Then we can just take the average of the both and aim for the middle of the two if the current position is like all the way over here still, if that makes sense. So the current position would be over here, the closest distance for it to be able to stop would be right here, and the distance where it would go to fully accelerate would be over here. Take the average of those two values and then you can just get the middle. So now we have a real correction x, which is just the correction x1 plus the correction x2 divided by 2, and then same thing for y. If the interceptor gets really close to our player, I'm just going to say that the cheetah gets the gazelle and it like kills it, or the proton torpedo explodes the ship or whatever. So let's call that radius like less than 40 or something. So here's the distance between the 2 points in Pythagorean theorem, you know. And then I'm just going to say to not correct the x or y, just aim straight for the position of the player at that point, since we just know that it's going to be really, really close. Aiming directly for position of the player doesn't really work normally, but it works really good when you're really close, obviously. Since the amount of time you get from point A to point B is so little, you can just actually just aim straight for the player. So we say correction x is equal to 0, correction y is equal to 0, say you're dead, and dead plus equal to 1, so we could say how many times we died. We need to keep track of dead originally, so let's just make dead 1 before the while loop even starts. Dead equals to 1. Now we need to correct our aim position. So instead of aiming for the current position, we need to actually instead aim for now that new position that we have corrected. Dx is equal to x1, subtract out x2 and add in the correction x. Same thing for the y. Now we need a distance between those two, and that's just an easy another Pythagorean theorem. Now let's keep track of the old velocity value, so let's keep track of an OGVX value, and this is of the enemy. Now we can update our velocity since we're keeping track of the original one. Same thing we did with the player's velocity, how we kept it as a constant speed. We're going to do the same thing with this one. We're going to make it EV, which is the 30 miles per hour we just set above, and then multiply that by the x component divided by the total size of the vector, which is the two components added together in the Pythagoras identity. EV times dx divided by r. That's why we made those dx and r values. Now we need to have the enemy actually change its position and change the acceleration, how it's going to be aiming for our player. But I don't just want to have it accelerate infinitely, so we actually want to have like a limit of the MA. We have if the VX2 minus OGVX, that's why we have to keep track of it, and then we can compare it to the MA value. Now we can say, oh, okay, it's all right. VX2 is equal to OGVX plus MA. And then you have 3 other possibilities for this, obviously, since if it's going too fast to the right, too fast to the left, and you can also do that with the same with the Y component. So we need to do 4 total combinations. If I was you, I would just go run through these in your head just to make sure they make sense to you. It's just limiting the interceptor from accelerating infinitely around and just going super fast. Now all we need to do is calculate our enemy's position. We do it the same way with everything else. We just multiply our velocity times the time incrementer. Now we need to have our 2 turtles go to their positions like we do with everything else. But let's just put in a boundary really quick, just because we don't want to have them flying around. It just makes it easier if we just have a box of 400. Well, for me at least it's 400 because it fits on my screen nicely. But let's say a bounding box, and then let's just set it equal to arbitrary value of 400 right now. You can change it later. We call it B box. That's what people kind of call bounding boxes, and in computer vision stuff they kind of call it B box sometimes. We have 4 sort of conditions. You kind of mix and match them, sort of get together. If the x1 is less than the negative boundary box, or if it's bigger than the positive boundary box, and we just switch it around and do that kind of stuff. All we gotta do is just flip those velocities at all the ends. We did this before though. So if you're confused on how to do this, go back to the old video. We did that stuff before on how to switch velocities around. Now we should go run this, and our predator should be able to sort of catch up to us. We have equal like accelerations and speeds right now, so it's not going to be super good, but it's still pretty smart. It can predict where we're going a little bit. Just remember that it's impossible to out-juke. Oh, I died. A way to be able to test it is let's just make a stamp of our player 1 at the very beginning. Let's do t1.stamp. Let's have us be really far away from the center and have the enemy in between us and the center, and let's try to get to the center of the screen again, to the stamped part, without getting killed by the enemy. Just remember that you can't out-juke it. The only way to win is to just make big circles and go all the way around. Oh, died. The controls are a little bit weirder than the jetpack simulator, but you get used to them after a little bit. So you just have to trick the guy around. But it is actually pretty hard to beat it. And this is if the Interceptor has the exact same stats as you. If you have like a little bit worse stats than it, then you're done any day. Especially acceleration. If the Interceptor has a better acceleration than you, then it can almost always predict very, very well, because it can change its acceleration very, very fast. It can just aim right at you. That's really powerful. What I want to do in the future is have something that would sit on the ground and toss little projectiles at the player. The player has to fly around up in the screen, and this thing would aim basically where the player would be. Because this is very good at aiming at where the player could be. It's like alright at actually intercepting people as well, but it's very good at aiming at where the player could be. But that's about it.